Hi, this is my explanation for numbers 5 and 6 on Chapter 5, WebAssign 2, Dynamics. Alright, so for number 5, let's see. The problem says, in an exciting game, a baseball player manages to safely slide into second base. The mass of the baseball player is 76.9. So we're going to write this over in our bank of knowledge. Mass is equivalent to 76.9 kilograms. And the coefficient of kinetic friction between the ground and the player is 0.54. Alright. So coefficient of kinetic is equivalent to 0.54. A, find the magnitude of the frictional force. Alright, so first of all, to get the kinetic friction, we need the normal force, because kinetic friction is the coefficient of kinetic friction times the normal force. Normal force is, in this case, it's equivalent to the apparent weight. And the normal force is, say this marker is resting on the stove. The weight of this marker is pushing down on the stove, and the stove is pushing back up, so the marker isn't falling through the stove, and the marker isn't flying through the air, because those are things that don't happen. It's at rest. It's just sitting on the stove, and it's at equilibrium. Here's the marker. The normal force is pushing up, and the weight is pushing down, and because the marker is not falling through the stove or flying through the air, we know that N is equal to W. Normal is equal to the weight. Alright, so now that we have that covered, now we know that weight is equivalent to mass times gravity. So our weight is equivalent to, in this problem, gravity is going to be 9.8 meters per second squared. In some of the other problems in this WebAssign, it's been like 10, and that's been a bit confusing. But in this one, it is 9.8. So 76.9 times 9.8. And this time I have my calculator with me. 76.9 times 9.8 is, weight is equivalent to 573.62. And that's in newtons. Alright, so weight, we also know, is equivalent to normal force, so we can just write equal to N there. And now we can solve for this equation. So I'm just going to write this in our bank of knowledge, because we may need this later. Normal is also equivalent to 73.562. There we go. Alright, and now we're going to solve this equation, so I'm just going to erase this. Kinetic friction is equivalent to the coefficient of kinetic friction, which we know is 0.54, times N, which we know is 553.62 N. So the coefficient of kinetic friction is 0.54 times 753.62 is 406.95. Alright, and so there's the part A answer. And then let's see, what does part B ask? Oh, by the way, this is in newtons, because it's a force. It takes the player 1.8 seconds to come to rest. What was his initial velocity? Alright, so now it gets a tad more complicated, because we are combining dynamics and kinematics, but it's really not as scary as it seems. It's really pretty simple. So we're just going to write the kinetic friction over here in our bank of knowledge, just so that we have that for future reference. So 406.95 newtons. Alright. So here is our baseball player. He is, I know he's supposed to be like sliding on his knees. I can't draw a stick figure on his knees, so I'm just going to do it like this. He is sliding into home plate, or it's not home plate, it's second base, but oh well. We're just going to, that's good enough. So then he's going and he's slowing down. So down here, they're going to be close together. And up here, they're going to be far apart. This is what he's doing. Alright, so first of all, we know that at the end he's going to be at rest. So let's see, I guess I'll make a second knowledge bank really small over here. So his final velocity is going to be 0 meters per second because we know that here he's going to stop, he's going to rest at second base. What else do we know? We don't know his acceleration. That we don't know. We're trying to find his initial velocity, so we're going to circle this one just so we know that that's the one that we're looking for. What else do we know? We know the time. Delta t is equivalent to 1.8, yes, 1.8 seconds, because the question told us that, and we don't know the distance that he's sliding. Alright, so you might be thinking, well, what can we do here? Because we have 3 variables that we don't know. It's really not easy to solve for 3 variables that you don't know. But we can find acceleration really easily with our information from our other bank of knowledge. So we know that the net force divided by the mass is equivalent to acceleration. We know that the mass is 76.9, so the net force divided by 76.9 kilograms is equivalent to acceleration. Oh, that's really slanted. What is the net force? This is something that it seems really scary to figure out, but it's fine. So we've got our baseball player. Again, this is just him in another iteration. He's got normal force pushing him up, and that is 753.62 newtons pushing him up. He's got 753 newtons pushing him down in weight. 0.62 newtons pushing him down. And then he's also got kinetic friction slowing him down. So he's got 406.95 newtons is his kinetic friction. Now, a lot of people would say, well, he's moving forward, so don't we have another arrow going this way? No, we don't. We do not have an arrow going this way because there is no force that's pushing him that way. Yes, he's moving in that direction, but he's slowing down. He's not actively like running in that direction or something like that. If that makes sense. There's nothing propelling him to go this way. No one's got like a rope tied to him and they're pulling him or something like that. He's slowing down. He has no force propelling him forward. So what is the net force here? Well, we know that these both are in the negative direction. To the left is negative, down is negative. So this is negative 753.62 newtons. So we can cancel these two out because they're equal. So now we know that the net force is equivalent to negative 406.95 newtons, aka the kinetic friction, because that is really the only horizontal force acting on him right now because the 2 vertical forces canceled out. So I'm going to clean some of this up a little bit just so we have more room to write. I don't think we really need this baseball player guy anymore. Alright, so if we solve for this equation, now we've got negative 406.95 newtons divided by the mass, which is 76.9 kilograms, is equivalent to acceleration, which is, let's see if we solve this out, you get negative 406.95 divided by 76.9 is equivalent to negative 5.29. Alright, so now we can write this in here for our horizontal acceleration. Negative 5.29 meters per second squared. Alright, so now we have enough variables to actually plug into one of our kinematics equations. So we need the equation that doesn't have time. So we're going to go with Vxf is equivalent to Vx initial plus Ax delta t. And this should look very familiar. We just finished doing an entire chapter on this. So it's really just the same thing that we did last time. It's just we had to solve for acceleration from over here. So his final velocity is 0. His initial velocity is what we're trying to solve for. His acceleration is negative 5.92 meters per second squared. And his time is 1.8 seconds. So if we solve this out, we end up with Vxi is equivalent to, what is negative 5.29 times 1.8. It is equivalent to 9.52. Now everyone can see like how like I multiplied this out to get a negative, and then I added this on this side and then moved it over there, right? Okay, algebra, we're good. Okay, so here is the answer to part B. Alright, now for question 6. I might split this into 2 videos if it's too longer. If I do, go to the next video for question 6. Alright, what is question 6? I did this one in Miss Kabati's room earlier. Let's see, a block with a mass of 56 kilograms, so I'll do the bank of knowledge on this side, just for fun. 56 kilograms is stuck in place on a rough floor. So we'll start our drawing over here. So here's our box, and here is our rough floor. I know there's not really any floors that look like that, but that's like just me exaggerating that it's rough. The floor's friction is characterized by a coefficient of static friction of 0.5. Alright, so its coefficient of static friction is equivalent to 0.5, and a coefficient of kinetic friction of 0.3. So its coefficient of kinetic friction is 0.3. A student pulls horizontally on the block with a rope. So we're just going to draw this for a little rope, and we're going to put a T for tension because he's pulling, and since it's a rope, it's tension. Assume gravity is 10 meters per second squared. Alright, so in this one, we're going to use 10. What force will she have to pull to free up the block? Alright, so first of all, we are going to solve for the weight. Just because, I mean, we want to make sure that we have the full picture here. We know everything that's happening with this block, and it will have weight going down, it will have normal force going up, and it will have static friction. So we're just going to solve for weight first, just so we can get these out of the way. Even though we may not need them for the first part, it'll be useful later. So weight is mass times gravity, as we learned. So weight is 56 kilograms times 10 meters per second squared, and if you solve that out, you get weight is 560 newtons. So we've got 560 newtons going down, 560 newtons going up. This is in the negative direction, this is negative. So if we were trying to find the net force, these would cancel out, but we're not going to worry about that right now. Actually, I'm going to leave the negative sign off now, because we aren't solving for net force yet. So now we want to find the static friction, which is what the question's asking for. So F of S is equivalent to the coefficient of static friction times the normal, which actually we needed that for this, so it's a good thing we solved that first. So this is equivalent to, actually I'm going to write normal in here, which is 560 newtons, and the weight in here, which is 560 newtons. So the coefficient of static friction is 0.5 times 560 newtons. Static friction is, kind of embarrassing, I'm doing this on a calculator, but you know, whatever, is 280. I'm always scared, like, I've done so many things wrong where like, oh, I know how to do math, and I just do it like by myself, and then it was something like really, really dumb, like, I don't know, like 4 squared is like 8 or something like that, and then I'm like, oh, I should definitely use a calculator. So anyway, so now we know that the static friction is 280 newtons. So we'll just write this in our bank of knowledge. And the question, it doesn't ask for static friction though, it asks what force is it going to take for her to move this block. So how hard is she going to have to pull? What is this equal to if we want to get this box to move? And to move this box, we really just have to equal the static friction. Like, you don't have to exceed it, although if you exceed it, it will also be moved. You really just have to get up to 280. So in order to move the box, she needs 280 newtons. Hopefully that makes sense. I'm not sure if my logic was like easy to follow there. Hopefully it was. But anyways, now on to part 2 of this question. Assuming she continues to pull with the force, what is the resulting acceleration of the block? Alright, so we already have a lot of information to go here. I'm just going to erase this. And this can be very misleading. Or actually, I'm just going to write 280 N in here. And then go over here, and for our tension force, we're also going to write 280 N. This can be very misleading, where you think like, oh, okay, since she's pulling with this, the friction is going to stay the same. So then we can just use our equation. The net force divided by the mass is equivalent to the acceleration. So then you might use the net force is 0, divided by the mass, doesn't matter what the mass is, and the acceleration is equivalent to 0. This is not correct, because if you're doing this problem, you're doing it based off of the static friction. Now the box is moving. It's not starting from rest. Now the box is moving along. So instead of having static friction, now it has, where's a good place to draw this? I'll just draw it in the middle. Now that box is a lot bigger than the other one. Now it has kinetic friction, pulling it this way, and kinetic friction is typically a bit less than static friction. So we've got our normal force pushing up, our weight pushing down, and we've still got our tension force going that way. So this is no longer accurate. This box, although the normal, the weight, and the tension are the same, we have a different kind of friction, so we can't use this one anymore. Oh, and I forgot to draw the bumpy floor. Well, the frictionless floor. For all we know, it's sandpaper. Anyways, so now we need to find the kinetic friction. So we know that the tension force is 280. We know that the normal force is 560, and we know that the weight is 560. So to find the net force, we only need one more thing. We need the kinetic friction. So kinetic friction is equivalent to the coefficient, all my tape's coming undone, the coefficient of kinetic friction times the normal force. Alright, so we have our normal force from before, so the kinetic friction is equivalent to the coefficient of kinetic friction for this floor is 0.3 times the normal force, 560 newtons. Alright, and if you multiply that out, you're going to end up with 0.3 times 560, oops, not negative 3, 0.3 times 560 is 168 newtons. So this is 168 newtons pushing this way. Alright, so now we need to find the net force. So for the net force, I guess if, like, typically you can do it kind of visually, like you can see like, oh yeah, well, the normal force and the weight, they cancel out. And then you can just kind of like see like, oh, I need to subtract 280 I need to subtract 168 from 280. And then you're going to end up with 280 minus 168 is 112. So this is the net force, 112. And if like you're really confused on how I got that, if you're like, wait, how did she just like cancel those out and all that stuff, then put a negative on the ones in the negative direction, so anything going to the left is negative, anything going down is negative. And then just add together all of these, and then you'll also get that number. Alright, so now that we know that, well, I'm not going to circle that because that's the answer. Too late. Oh well. Now that we know that the net force is 112, we can use the equation net force divided by mass is equivalent to acceleration to finally find the acceleration. Actually, I'm going to write that down first because that's what we do. We write stuff down. I also didn't write down the kinetic friction. I'm almost done with the problem, but just on the basis of principle. 168 8 newtons. All right. So we know that, I'm going to do this in a different color because celebratory, it's the last part of the problem. We'll do green. So we know the net force is 168 newtons divided by the mass, which is still 56 kilograms. The mass hasn't changed. Probably won't change. So then if we do this out, 168 divided by 56 is 3. The acceleration is 3. This doesn't seem right for... Oh, oops. Sorry. Okay, so I used the kinetic friction instead of the net force. So, oops. Ignore that. That was a mistake. We need to be using the net force. And then we get 112 divided by 56 is 2. 2 meters per second squared. Alright, hopefully that was helpful. If you have any questions, I will be in the caf tomorrow morning at like 7 a.m. So I guess that's all. Bye!